Hi, thank you for joining this talk. This talk is about the latest new release in Apache Flink, an API called Stateful Functions. During the first day of the virtual conference, Stefan had already gave a great overview on what the project is all about and its motivation. So this talk will just be an extension to that, focused more on the technical deep dive. My name is Gordon. I am a PMC member in the Apache Flink community and a software engineer at Liberica, currently working on the Stateful Functions project. So, a quick overview of this talk. We have quite a bit to go through. We'll go through a quick recap of what Stateful Functions is, then we'll thoroughly go through the SDKs users develop with a goal in mind so that you may start developing your own Stateful Function applications. And after that, I'd also like to show you a really cool demo that I prepared of a stateful serverless application implemented using Stateful Functions. I will demonstrate some nice characteristics such as zero downtime upgrades, which you'd expect in serverless deployments, but here with consistent state. We'll go through the details of that shortly. To help you take in the key benefits of stateful functions better, we'll also take a peek at the runtime of how things work. Finally, I'll conclude this talk with a look at what is up ahead for the project. So what exactly is stateful functions? Simply put, Stateful Functions is an API or framework on top of Apache Flink that simplifies building distributed stateful applications. Users will develop their applications by implementing several services or what we call functions, which are basically small pieces of code or logic that represent entities in an application. So you can, for example, define a function type that represents a user, with a single instance of that function type representing a single user in your application. The function instances are invocable through messages, and they don't consume resources while inactive, or simply put, when they are not invoked. What that means is that the runtime can run infinite amounts of function instances within a fixed finite set of resources. We'll go into details of how that works later when we look at the runtime internals. Another really cool thing that came along with the new Stateful Functions 2.0 release is multi-language support. Functions can be implemented in any programming language that basically can handle HTTP requests and responses. Again, we'll go through the details of how the Stateful runtime handles and supports this later. Next of all is dynamic messaging with consistent state. So what dynamic messaging means is that functions can arbitrarily and randomly communicate with each other. You don't have to predefine data flows as DAGs essentially. Another important aspect of the messaging is that function messages each other, so functions message each other by logical addresses. There is no service discovery needed. All a function needs to know in order to invoke another function is the type of function and an ID of a function instance that it wants to invoke, which is essentially the logical address. We'll go through that as well later. Now, all of this messaging can be done with exactly one semantics. So functions instances that can keep local state, while the runtime makes sure that messaging and state updates are integrated so that users can have out-of-box efficient consistency across the event inputs to the application. Here we can see ingresses, application state, and outputs delivered from the application via event egresses. And if you are familiar with Flink, coming from a Flink background and knowing that stateful function applications run on top of Apache Flink, you probably would have already guessed it, that the strong consistency semantic provided by stateful functions is realized based on Flink's distributed state snapshotting model. So the runtime takes periodic consistent snapshots of all functions' instance state, as well as the corresponding positions in input ingresses and transaction state of egresses. And those snapshots form a consistent snapshot of all, form a consistent distributed snapshot that is persisted into mass storage periodically, such as Amazon S3 and HDFS, etc. For people not familiar with Flink, what this basically means is that function state consistency and fault tolerance is not handled by a database, but instead a stream processor, and all you need is blob storage to store the periodically created state snapshots. The final notable thing that I'd like to mention is how distributed stateful applications implemented using stateful functions can seamlessly take advantage of modern serverless platforms like AWS Lambda or Kubernetes deployments, giving you the operational management benefits of these platforms like rapid scalability, scale to zero, and zero downtime upgrades. This is all possible due to some runtime design choices, as you can see here in this diagram. A stateful functions application uses a Flink cluster for message routing and state management, while allowing the actual functions containing application logic to be deployed in a separate standalone service, separate compute tier. What this gives us is that the runtime keeps a logical collocation of compute and state for consistency, but at the same time physically separated deployments of the state tier, being the Flink stateful functions cluster in this diagram, and a compute tier which is essentially stateless because all state access and updates are integrated as part of a function invocation requests and responses. Don't worry if you don't know what that means exactly yet. We'll go through that later in this talk as well. So, alright, now we will start going into some technical details, taking a closer look first at the SDKs users program with. First, to understand the characteristics of the different flavors of SDKs the project supports, you'll need to understand that stateful functions supports different kinds of functions based on how they are deployed. On the left here, we have what we call embedded functions, and on the right, remote functions. What embedded functions are is they run within the Flink stateful cluster worker JVMs. Much like how operators of a Flink streaming job are passed inputs, embedded functions are invoked directly with messages and have local state access. The restriction, of course, is that these type of functions must be implemented in JVM languages. Currently, embedded functions is supported with the Java SDK. And on the right, remote functions. The difference between remote functions and embedded functions is that remote functions are deployed separately and external to the Flink stateful cluster as a standalone service with an exposed HTTP endpoint. So the main difference is that function invocations go through remote HTTP requests. And as I've previously mentioned, state access and updates are part of the HTTP request-reply protocol defined between the cluster and the service endpoints. Essentially, any language that can handle HTTP requests by setting up an HTTP server can be used to implement these remote functions by implementing the defined request-reply protocol. Currently, we ship a very slim Python SDK that already implements this HTTP request-reply protocol that you can readily use already. The conceptual building blocks users work with are exactly the same between these different flavors of the SDK. So I'll go through one first and then just briefly go through the other to cover the main differences. Let's start with the Java SDK, or embedded functions. So, let's take a look first at implementing the functions itself, the main core building blocks of the applications. So essentially, when functions are invoked, they can send messages to other function instances, including itself, send messages to other egresses, or persist some local state. There are also some other powerful things they can do, like schedule asynchronous operations or send delayed messages, but we won't cover all of those here. The above is the essentials of what a function does when invoked. This here is a very simple implementation of a Java stateful function. It's called greet function. What it does essentially is it accepts events which are greet requests, and then it builds a personalized greeting for the user sending this greet request, and then it sends this personalized greeting to an email sender function which is in charge, let's say, of sending an actual email to the user using the created personalized greeting text as content. Okay, so you can imagine that for every user in the application, there always exists an instance of this greet function class, which handles requests for that single user. Each function instance has a unique logical address, which consists of a type of a function. In this case, the type would be a greet function, and then a unique ID, which in this example is, for example, a user's unique UID. So here you can see how a function sends a message to another function. It basically, to invoke another function, you send a message to a function by sending it to the target function's logical address, which we just previously mentioned consists of a type and the ID. For example, if you want to invoke this greet function itself, an instance of this greet function itself, another function can then do context.send and then the address, greet function type, and then let's say the user ID is John Doe, and the message. What this does is it invokes the function instance of the logical address, greet function John Doe. Okay, and on each invocation will provide a context for the current function call. As we just seen, you use this context to send out messages, and this context is also used to query information such as this function, invoked function instance's own address, and the caller's address, etc. Next, the most powerful aspect of stateful functions is that functions can have, durable state. Here's a snippet of what the create personalized greeting method we've seen in the previous example might actually be doing. All we're doing here in this code snippet is keeping track in durable state how many times we've seen a user and then create a special greetings text based on that count. Okay, so in this highlighted code, you can see how persisted state is declared as a field variable of the functions class. Now, when this function is loaded by the runtime, it will discover this declaration and then register the state to be managed for consistency and fault tolerance. From there on, you can then access and update durable state like as you would working with a local field variable. Here we're only showing one type of state primitive called a persisted value, which is basically just a value. There are also other supported primitives like an append-only buffer structure or table-like map state structure, each having better performances based on your access pattern. We won't go through all of those here, but good to keep that in mind when writing your own application. Next up, after implementing multiple functions, each representing a separate entity in the application, what you want to do is then define what we call a module. A module is a bundle of functions that are loaded by the runtime when you deploy your application and make them available to be messaged. And a complete stateful function application can be composed of one or more modules. So what you see here is a definition of just a single module of embedded functions. And this is what you basically do here. It's basically implementing an interface called the stateful function module, and this interface contains of a single method called configure, which passes you a binder, which you use to bind functions to the module. Modules are discovered and loaded by the runtime using the Java service loader, actually. So what you need to do in the end when bundling all these function classes and module class into your build jar, a service provider configuration file must be bundled with a build jar. Here I'm using an auto service annotation, which is provided by Google, which generates this configuration file automatically. But you can also do this manually if you don't want to use this auto service dependency. And so as you can see here, we're binding two different functions to their specific types. So we're binding a provider of greeter function instances to the greet function type, and then binding a provider of email sender functions to the email sender function type. And this is how the runtime knows what function instances to invoke for a given address, which contains the type of the target function. The only thing missing in the whole picture now is how to interact with your functions in your application from outside the application. And how we do that is via what we call event ingresses and egresses. So ingresses allow the outside world to invoke your functions, while functions may emit events back to the outside world through egresses. We currently support out of the box two different kind of egresses, which is Apache Kafka and the AWS Kinesis. We chose to implement these two first because they support Flink's fault tolerance model really well, allowing consumers to roll back and restart consumption from a specific position consistent with restored state. Underneath, they're all just based on Flink's Kafka and Kinesis exactly once connectors, which you should be fairly familiar with if you come from a Flink user background. I won't go through the actual code of how you bind these ingresses and egresses because of limited time, but essentially you bind ingresses and egresses with a modules binder. So you bind function providers and then bind ingresses and then bind egresses. Okay, so we've covered all the essentials of the building blocks of the stateful functions application using the Java SDK as reference. Next, we'll take a look at the Python SDK with a focus on what is slightly different there, with its implementation based on the remote HTTP request reply protocol. So one main difference comes from the nature of how remote functions can be implemented in any language, and therefore requiring a universal format for messaging between the functions. This universal format was decided to uniformly be the protobuf any type. If you're not familiar with protobuf, what any type is, it's a generic format which wraps a protobuf message in a serialized form plus a URL describing the type. And what receiving functions do is they unpack the any messages they receive using the language-specific protobuf libraries. So this is just an illustration to explain that. On the left here, we have a Python remote function, and on the right, some other function which is sending messages to and receiving messages from the Python remote function. So as you can see here, this other function is sending any message to the Python remote function with the type URL and the serialized message bytes. And in the Python remote function, what it needs to do is use the Python protobuf library to unpack this to a specific type, which here is a GREET request. And when the remote function wants to send out a message, it also needs to use the protobuf Python library to pack its response, which let's say it's a GREET response type, into an any and then sends it out to the other function, which on its receiving side needs to also unpack this to the type that it works with. Okay. The same goes for state types, because the Flink stateful cluster runtime needs to be able to handle state written by multiple different languages. The state types also needs to be this universal recognized type, which is this protobuf any type. And Flink simply stores state in the state backends in their serialized form as wrapped as is in the any objects. So the Python SDK, instead of letting you working with these any messages and unpacking all the time, it provides utility methods that allows users to directly work against specific protobuf types and does the packing and unpacking automatically for you. So this is really just a re-implementation of the GREET function, but now in Python. And as you can see here already, a convenience syntax. So you can just say the input, my inputs are GREET requests, and they would automatically be unpacked as GREET requests within the function. If you don't specify the GREET request, what you get as the input is any objects as the input messages. And when you send out messages, you can also automatically pack protobuf messages into any's by using this pack and send method, also on the context. So you also use the context to send out messages. One little difference in the Python SDK, for function types, the way you define it is using this compact string format, which with a backslash, and in front of the backslash is the namespace, and after the backslash is the function type's name. Okay, now state persistence. So with Python, the difference between the Java SDK to actually declare persisted state, to actually access and update persisted state is not via a field variable, but you do it via the invocation context, as you can see here. So context.state scene count gets the state of scene count, and then you can also set the state via the context. Okay, and as you can see here, underneath everything are protobuf any's, but you can use these unpack and pack methods to work against specific protobuf types. And finally, after the last step of implementing remote functions is exposing these functions via an HTTP service endpoint. The Python SDK also ships constructs for you to do that conveniently with any HTTP web framework of your liking. So you bind multiple functions with their function definition. As you can see here, we use this stateful functions construct that is shipped with the Python SDK, and you bind this GREET Python function with the demo greet function type, and then you bind the send email function with an email sender function type. Then what you do is you register all these binded functions with a request reply handler, which is also a shipped construct. What this handler does is it basically dispatches invocation requests sent via HTTP to bound functions. And then the resulting side effects of these functions, which is resulting outgoing messages and state updates, are encoded as a single HTTP response that is sent back to the Flink cluster as part of the service response. Okay, and finally, you expose this handler with your favorite HTTP web framework. And here we're just using Flask as an example. Okay, and last of all, like embedded functions, you also need to bundle functions, ingresses, and egresses as modules so that they may be loaded by a stateful functions applications. Now, with remote functions, modules are simply defined using a complex textual YAML definition file instead of some language-specific class. Okay. So here's just a section of how you would define a function in this YAML module definition. You would define what function types are bundled by the module, and you would also specify the kind of remote functions that are bundled. Currently, only HTTP is supported, but we're also planning to support other protocols like gRPC. As part of the HTTP functions definition spec, what you also need to specify is the endpoint of the service, and then states that it will need to use. So the service endpoint needs to be here so that the Flink runtime needs to know what endpoint to invoke for this HTTP function. And the states needs to be declared for this HTTP remote function because state values, as we know, it needs to be eagerly declared because state values are always bundled along with the invocation requests when invoking these remote functions. So this needs to be there for the Flink runtime to know what to do when invoking this function, essentially. We won't go through the ingresses and egresses here because of limited time for this talk. You can all find all of those in the Flink documentation, and we ship Kafka ingresses and egresses for YAML definitions as well. So you can just use textual YAML definitions to define Kafka ingresses and egresses. Now, wiring it all together is to package multiple modules into an application that you can finally deploy. So, as we just previously mentioned, a stateful function application consists of multiple modules. You can mix embedded modules and remote modules. And what this means essentially is that you can have multiple functions in your application, each with their own language implementation. Now, the runtime loads all functions, ingresses, and egresses defined by all modules, and all loaded functions can then message each other arbitrarily with exactly one semantics, and all loaded ingresses can route messages to any loaded function, and any function can send messages to any loaded egress. And so to illustrate this, what here is we have a whole stateful function application of egresses, ingresses, and functions, and all of this really could be provided by different modules. And for example, the ingress from module A can then message a function from module B. And what you want to do to get your application ready for deployment is then bundle all these modules into a single application image for deployment. So here's an example Docker file of this application image. You would base this on a base image, stateful function distribution image, that contains already all the statefun and Flink dependencies. And then you simply copy all modules. If it's an embedded module, it would be a jar. And then if it's a remote module, it will be YAML into the modules directory. So what you can see here is that we're bundling an embedded module and also a remote module into this application. Now finally, when deployed, what this application looks like is, first of all, you would deploy remote function as standalone services behind endpoints. So this has nothing to do with the Flink statefun cluster yet. And then using the image that you just built, you will start deploying the components of your statefun cluster. So you will first deploy the master, and how you would do that is simply docker run, and then you specify an environment variable which specifies that this is to run as a master, and then you would deploy multiple worker containers. And when you deploy these worker containers, it would also run the embedded JVM functions, the Java functions, with the JVM worker, with the worker JVMs. Okay, so now I want to show you what I think is a really cool demo of a stateful serverless app, in which I'll be deploying serverless Python functions using AWS and in conjunction with some Java embedded functions to see all of this coming all together. The scenario for this demo is a simple shopping cart example. So we have two separate services here implemented as functions. First one is a shopping cart where each instance stores items of a user's cart in state here. And the next we have an inventory service in which each instance of this inventory function type stores state of an inventory, for example, the number of remaining items of this inventory in stock. So the interaction of these two services is roughly when the when the shopping cart function gets events from an ingress saying add items to cart, it requests reservation for that item with the inventory function. Now the inventory function then checks availability of this item based on the state, for example, how many of this item is remaining, and then it reserves this item and then replies to the user's shopping cart about the availability of this item. Now, on being acknowledged the availability of the item, the user shopping cart function will then update the user state to contain that item in the cart. Now, in this scenario, inventory stock and requests bookkeeping needs to be accurate. You wouldn't want to have false accounting of number of items sold to all users, right? So what this essentially means is that you'll need consistent messaging and state between these two services, the functions of these two services. Another aspect of my scenario is that services could be implemented by different teams, each with their own language preferences. For example, the inventory service is implemented by, let's say, a platform team which likes to use Java. And the shopping cart service implemented by a products team which happens to prefer Python. Each team would bundle their own modules, and then these modules would then eventually be packaged together as a single application. Okay. Now the actual deployment of the demo looks like the following. A Flink stateful cluster is deployed locally on my computer using Docker Compose. It would deploy the stateful master and all the workers, which also has the Java embedded inventory service functions running within it. And then the shopping cart Python functions are run using AWS Lambda behind AWS API Gateway, which provides the service endpoint for these Lambda functions. If you're not familiar with AWS Lambda, it is essentially a functions as a service, having all the serverless benefits, such as rapid scaling, scale to zero, and zero downtime upgrades of the functions, which we'll see shortly. I'm only using AWS Lambda to demonstrate this because I'm personally familiar with the service, but this can be any kind of deployment really, such as Kubernetes deployment, which you might have seen in the keynote on the first day of the conference. And finally, just to round up the fact that I'm heavily using AWS for this demo, I'm using AWS Kinesis as the ingress and egress of the shopping cart user events. Right, let's take a look at the demo code. So as you can see here, we have an inventory function implemented in Java, and we'll also take a look at a shopping cart function implemented in Python, and we'll be bundling these functions into a single stateful function application image for deployment. Now let's take a look at the inventory function first. So this invoke method is essentially what this inventory function is doing, and it expects messages of request item type, and it handles these request item. Now, but all it is doing is handling this item request is determining the item availability and then changing state to keep track of the number of requested count of this item, and then replying the request with the item availability. And we bind this inventory function into an inventory module. And all this module has is this inventory function defined to bind it to its specific type. Okay. Now let's take a look at the Python function. So the Python function has a card function, and all it is doing is, depending on the input message, let's say it's a card event. If it is a card event, for example, adding to a card or checking out a card for payment, or if it's the item availability event, which is a response from the inventory service, it behaves differently. Now, we won't go into the details of these message handling, the logic of these message handler methods because of time constraint. But you can imagine what it basically, what it does. It's quite simple. Okay, now, so we bind the functions to the request reply handler, and then we expose this request reply handler through AWS Lambda. So if you're not familiar with AWS Lambda, what it essentially does or how it works is define a function which is invoked when this Lambda function is invoked. And let's say you expose this Lambda function through AWS API gateway. So when this API gateway is invoked, is sent a request, this request is forwarded to invoke this Lambda handler, which forwards that request to our stateful functions request reply handler, which has this function bind. Okay. Now let's take a look at the module definition. What is interesting here for the shopping cart? Okay, so as you can see here, we have the shopping cart function binded to the shopping cart module, and we define the endpoint. Now we get this endpoint by exposing the AWS Lambda function through the AWS API gateway. So this is the endpoint of the API gateway, and we'll also eagerly define the states that this function will use. Maybe what's also interesting is, so we're just using the shipped Kinesis YAML configuration ingresses and egresses for AWS Kinesis. Now, none of this actually includes any other external dependencies. This is all just textual configuration and definitions. Okay. Last of all, let's take a look at this. So we're deploying the stateful function cluster locally, right? We're deploying the master, the worker, and the workers. So this is briefly what the master service would look like. You would say, okay, I'm running this as a master, and I'm running workers as workers. And these services are using the application image, which is defined here. So this is also, should be familiar with this. We've seen this already. So this Docker file is just built on top of the base Flink stateful Docker file, and we're bundling the inventory module and the shopping cart module as part of this single application. Alright, now let's see everything in action. So what do we have here? I've already bundled the application image and built the application image, and now all we need to do is just start the local Flink stateful cluster with our image. So Docker compose up. Now while this is being brought up, let's take a look at the right web console here. So this is the AWS Lambda console. I've already uploaded the shopping cart code onto AWS Lambda. I've also already created the AWS Kinesis for Ingresses and Egresses. Now, as you can see in this illustration here, I have a stateful functions. If this is demo, this should actually be better named shopping cart, and this is sitting behind an API gateway endpoint. And this is the code that we're actually just looking at. And with Python, alias Lambda, you can actually just edit and look at the code inline. Okay, so let's invoke this. Let's take a look. If you can, it's actually a bit small, but you can see here we're already starting to perform checkpointing for this stateful function application. To demo this, I've written some scripts here. Okay, consume scripts, consume receipts. So what this is doing, it is continuously polling the Kinesis egress, receipts egress. And now let's add some user card events into the ingress. So let's say I'm adding a user card event for user Gordon, and Gordon wants to add some socks, and wants buy 5 socks. Okay, so nothing happens yet from the receipts because we should not have checked out yet. And let's say I also want to buy some pants. I want to buy 3 pairs of pants. Okay, now after that, I want to do a checkout. So user Gordon does a checkout. This is just sending protobuf messages to the Kinesis ingress. And checkout, we should see a event here. Okay, cool. So we've received a receipt from the received egress right now. Okay, so that's pretty good. And we can also add more users, add more inventories into the cards and do more checkouts. So let's do one more thing here. I want to demonstrate how this all works with serverless applications, zero downtime upgrades. So here we see a bug. Okay, so this receipt, it doesn't have the user ID in the receipts event. We want to add the user ID. So this, let's say this is just a bug that we discovered. And okay, I want to fix this bug. Let's go to, it should be in message handlers, handle the checkout event, but the receipt event that I built, which is sent to the egress, doesn't have the user ID specified. So receipt user ID, and I'm using the address to determine the user ID. And okay, now we've fixed the function, fixed the bug, and let's just save. So this is redeploying a new version of the alias Lambda function. It takes a few seconds, but while this is being upgraded, the Flink stateful cluster is not being stopped. It's just running independently by itself. So okay, now this has been finished upgrade. So let's add, I don't know, another user, Joanne, add a hat. Let's say I want to buy 5 hats. Okay, Joanne wants to buy 5 hats. And then what Joanne does is a checkout. And now this function, the receipt should have a user ID because we've already fixed the bug. Okay, so right now, okay, so as you see, now this new receipts event has the user ID Joanne in it. Okay, so we fixed the bug without stopping the Flink stateful cluster. Okay, now one last thing I want to demo is actually fault tolerance. So let's do one more user. Let's say, okay, Eagle. Eagle wants to buy, I don't know, he wants to buy more socks, 7 socks. Okay, now what I want to do here on the bottom right, it's a bit small, but you should manage. Docker compose, I want to restart worker 1. Okay, restarting worker 1. Now what this basically does is it kills one of the workers, and as you can see here, the job is actually cancelled now, and it's actually restarting. It's being restarted. Let's wait for it a bit. It will take a few seconds for this job to restart. Now, as we all know, stateful functions, it provides fault tolerance and state consistency for your functions. So what we should expect after this restart is done, if Eagle checkouts, it should still have the socks in the shopping cart inventory state, right? Should still be in there. Okay, so let's wait a bit. Not sure if it's running yet. Okay, I think it is running. Yes, it is running now. It is running again. Okay, now let's check out Eagle's card. Okay, and we should see the socks still. Yes, okay, so here we still see that Eagle's addition of the socks to the items inventory to the user card is still persisted and is fault tolerant, even after we restarted a worker. Okay, so after the demo, I would like to take you into a guide through of what the stateful functions runtime is like and things that it does. So throughout this talk, I've been talking about some runtime characteristics, which we'll go through the details here. One of these characteristics that I have been constantly bringing up is how function instances are virtual, and they don't consume resources unless they are invoked. Second of all, is the interplay between compute and state, or more specifically, how the runtime provides consistency for messaging and state while at the same time allowing functions to be physically deployed external to the Flink stateful cluster. Now, to understand all of this more easily, it would be best to first understand how a stateful functions application runs as a Flink streaming graph. We'll first focus on how dynamic messaging works within the underlying Flink streaming graph. So here, as you can see, all loaded ingresses are translated to Flink source operators emitting the input messages, and routers are translated to chained flat map operators. The router flat map basically takes the input messages emitted from the ingresses and then transforms them to internal event envelopes, which essentially just wraps first the message payload and then the message's destination function's logical address. Envelopes are essentially what are the onward data types for all messages flowing through this underlying stream graph. Now, the stateful functions runtime then runs a function dispatcher operator, which runs instances. You can think of running instances of all loaded functions across all modules. In between the router flat map operator and the function dispatcher operator is a key by stream partitioning operation using the target destination address as key. And this is essentially how messaging is done in stateful functions. Underneath is just a network shuffle of the envelopes that routes the envelopes of the same address to the same function dispatcher Flink subtask. Okay. Now on the receiving end, the function dispatcher then extracts the target function addresses from the envelope, loads the target function instance, and then invokes the function with the wrapped input message payload, also in the envelope. Now, the next part is how functions then message each other, or simply how the function dispatcher subtasks send messages to each other, right? This is done by co-locating each function dispatcher with another feedback operator, so that outgoing messages sent from functions is also going through a network shuffle using the target function addresses as key. When the feedback operator receives an envelope, it puts the envelope into a process-wide mailbox, which the co-located function dispatcher operator also has access to. So let's say function 1 here wants to send a message to another instance of function 4. Now let's say that based on the partitioning, that target instance of function 4 lives in a different partition. So what happens then is that the outgoing message is shuffled to that subtask's feedback operator. So let's say function 1 sends a message. It is partitioned and sent and shuffled to this feedback operator. And then this is provided to the local function dispatcher operator using a local feedback mailbox, which the function dispatcher operator also has access to. So this is how functions message each other. It goes through a function, goes through a network shuffle, is consumed by a feedback operator, and then feedback to the dispatcher operator using a local mailbox. Okay, now I want to take a closer look at the internals of the dispatcher operator itself. With this, you'll be able to understand how exactly our function instance is virtual. Now, within the dispatcher operator, there is essentially two important components. First is a registry of loaded functions here. Now, this registry consists of a singleton instance per function type. Now, notice it's not per logical address, but just an instance per function type. The second on the bottom here is this Flink's state backend. And each row in this state backend, the key is the logical addresses that are partitioned to this specific dispatcher operator instance. Okay. Now, what happens on receiving an envelope, as we previously mentioned, is that the target function type is extracted, and the singleton instance of that function type is retrieved from the registry. So if this is first access to that function type, then the singleton instance will be created on the fly with the bound function providers that you bind using the modules. Next is the load state for the current invocation. So if you're familiar with Flink, internally in Flink, this is really just a key context switch on the state backends to using the logical address of the target function instance. So when invoking the function and the function accesses or updates state, all it is actually doing is reading and writing to a specific row in Flink's state backend. Here, we're demonstrating a remote function as the target, with the function's compute logic living as a standalone service. So when we are invoking the function, now after loading the state and we want to invoke the function now, what happens is that an async request will be sent to the function's HTTP service endpoint, as defined in the YAML module definitions. There is a request-reply protocol in place here, which defines that the request body wraps the input message, state for this current invocation as loaded from the state backends, and also invocation context about information such as the invoked logical address and sender's logical address, etc. If a function is actually an embedded function, the only difference for this illustration here is that the compute logic lives within the same process and will then just be invoked directly and has direct access to the state backend. But for remote functions, as defined by the HTTP request-reply protocol, the state updates are bundled in the response from the service, as well as any outgoing messages that the function wants to send to other functions or egresses. Now, on receiving this response, the dispatcher operator then accordingly updates the corresponding row in the Flink state backend and sends outgoing messages to the output mailbox, which then, as we've previously seen, the output messages gets routed to a feedback operator and eventually dispatched to its target function. So this state update operation, one thing to understand is this state update operation and emitting events is handled as an atomic operation in Flink. So as you can see by now, the only resource that these virtual function instances take up is storage space in the state backends while they are inactive. And with Flink supporting out-of-core state backends like RocksDB, which maintains data off-heap, the only real limitation for how many function instances you may have in an application is therefore essentially just disk space. The more logical addresses you may have, or in Flink terminology, the size of the key space, the more storage you will need to maintain function state. To finalize all of this, at a high-level overview of the runtime, messaging between functions and services within a stateful functions application is really just streams of envelopes being routed between different partitions of a Flink cluster. So let's assume that both the shopping cart service and inventory service in my previous demo are remote functions behind standalone endpoints. The Flink stateful cluster reads events from the ingress, which gets routed to a specific partition, and that message is sent to the shopping cart service. And when at the user level, a shopping cart function wants to send a message to a inventory function, this results in a message getting routed through Flink, potentially to another dispatcher function, and then this dispatcher partition, and then this dispatcher partition then invokes the inventory service through HTTP. Okay, so that was the last detail I wanted to cover, and that brings us to the last part of my talk, which is to just quickly go through some interesting plans up ahead for the Stateful Functions project. First thing is to stabilize the remote function HTTP request reply protocol as a public interface. So right now it is already public, and you can already start implementing new language SDKs based on the protocol, but we wouldn't completely say that it is completely stable yet. So by stabilizing it, we're hoping to allow new language SDKs to be rapidly developed for a richer language SDK ecosystem around stateful functions. Next, the second point is a gRPC-based remote function protocol. Now, right off the bat, even if we're re-implementing the same request-reply protocol, this would just be a more efficient transport that can provide higher throughput than HTTP. But also, RPC-based protocols will allow us to have bidirectional requests between, so from the Flink cluster to the remote function, and also from the remote function back to the Flink cluster. And this bidirection will allow state to be lazily fetched. So in contrast to the request-reply protocol, where state is eagerly fetched on every invocation request as part of the protocol. Now, third of all here is well-defined service interfaces for functions with gRPC. Now, the community is also thinking about this. So as you can have seen already, right now the interface of a function is really just an invocation, an invoke method, where the function can get past any arbitrary object as input, allowing functions to define clear service interfaces will really improve the composability of function interaction. Next up, the fourth point here is a slightly smaller scoped thing. You can expect more messaging patterns to become available, such as a native pub/sub messaging primitive, where functions can publish events to topics living within the application, and have other functions subscribe to the topics. Again, it's just another thing that improves how functions and services can interact with each other. The second last thing here is something that is already somewhat highly requested, is to allow stateful functions embeddable within the Flink streaming job, so that Flink libraries like Flink table, Flink CP may be also used in conjunction with stateful functions. Last but not least, the last point here, and actually what I think is the coolest upcoming thing, is being able to bootstrap and analyze distributed state of your applications using SQL. So if you really see stateful functions as an event-driven database, the stateful cluster as an event-driven database, with databases, you'd expect to be able to dump in and populate your database with initial data, and also analyze the data in your database. This is actually all possible right now, only that in Flink terms, this database dump is really just a distributed state snapshot in Flink. And you can use Flink State Processing API, which is in Java, to bootstrap and analyze state in that snapshot. For full multi-language support storing and stateful functions, we're thinking about extending that to SQL, so that you can bootstrap function and service state, like dumping to a database table with SQL, and also analyzing point-in-time state with SQL. Right, last but not least, finally, some resources for you to consider. So if you have any questions or discussions about features you want to reach out to the devs too, feel free to reach out to the devs on the Flink user and dev mailing lists. We'll be very happy to hear from you. And here's some links about from the Flink website about what is stateful functions and documentation of the SDK and everything about stateful functions. And of course, the source code repo for the project. Okay, so this wraps up my talk, and thank you a lot for joining. I hope you've have some quite good takeaways.